So one of the things that are really nice about binary search trees, right, is that, if we have a perfect binary tree, then there are, right, it was the 2 to the n is equal to the number of leaves in depth n, right? We have that exponential growth. But in reality, right, trees aren't going to be perfect, especially binary search trees, right? Binary search trees, as opposed to just regular binary trees, have more requirements on where we can place nodes. It's not always going to be perfect. Perfect is not always possible. But again, the bushier, the wider, the more full, however you want to say it, the wider, the bushier the node, the better the searching efficacy is going to be, right? The more it is close to perfect, the faster we're going to be able to search, and the more we're going to be able to have that big O of log n speed. So that has to do with the concept of balancedness. Now, I'm not going to get too in depth, and I don't even think the author states the definition of a balanced tree, but something is balanced if the height is basically kind of as small as possible. I'm not even going to write that definition down, but it's a way to think about it. That's what you want to think about for balanced. Is the height as small as we could have made it? The smaller the height relative to the number of nodes, the more balanced it's going to be. One of the definitions for balancedness that we're not going to focus too much is that the depth of the left and right subtrees for any node only differs by 1 or less. So this is a very common definition for balanced. It doesn't even honestly have to be 1. Sometimes this number does change for some definitions of balancedness, which is why I'm not focused so much on the exact definition. But the idea is, what are some trees? Let's look at some trees. Well, let's actually look at some binary search trees. So here we go. This was not a binary search tree, but binary search tree over here. Look at any node, left and right subtrees. Is the height of that subtree either equal or different by 1? Yep. Each of these subtrees have the same depth. Okay, these subtrees are only 1 apart, so that's good. These subtrees are only 1 apart. Yeah, this is a balanced subtree. Okay. Over here, this is not a balanced subtree, right? Let's look at Jessica's subtrees. The left subtree has height 3. The right subtree only has height 1. So this is not balanced. There are some ways that we could rebalance it by moving some stuff around. And we could really go to the extreme of this, again, in thinking of like search optimality. And I forgot to actually paste this over here. But here's another tree. Let me pull it up real quick. Here's another tree that is not quite balanced. So let's, again, look at this situation. Let's move these into a new binary search tree. Like so. This is a binary search tree. This is as unbalanced as you can get. Okay? It does follow the binary search tree requirement, but it's not balanced and it's not going to be fast, right? If we're trying to search, it's just searching alphabetically. This is not a balanced tree, right? The left subtree of Ben is 0. Height, the right subtree is like 7 or 6. I can't count. All right, so again, searching through this would not be quick at all. This would really just be O of n, big O of n. So that would not be balanced, right? The depth of the left and right subtrees differs by a lot in that one. So there's a few ways to kind of deal with making sure things are balanced, and that's what we're going to talk about next. Again, not going to go super in depth in this, just ways to think about it. There's 3 ways to avoid this issue of getting unbalanced trees. The first one's my favorite. It's just to ignore it. Because realistically, realistically, when you're making binary search trees, this is not going to happen. It's possible, but assuming there's some element of randomness when you're creating these binary search trees, like you're not hiring people in an alphabetical order, for example, or something like that, this is very unlikely to happen naturally. So a lot of times we can just, wait, where'd my notes go? A lot of times we just, I don't know. A lot of times we just ignore it and say, well, we're going to construct these. They're going to just become more or less balanced. The second way is to periodically rebalance. Okay, so let's say, every once in a while, maybe we're taking our server down for maintenance or whatever. We're going to spend some time and rebalance our tree. If we're thinking about things alphabetically, we can make the root of our node the middle. And then we choose its child, the middle of each half, right? So if we think of the A to Z here, we would make the root of our tree somewhere in the middle. And then we'd make the left child somewhere over here and the right child here. And each of those would have left child like here, you get, and so on and so forth, right? Have a left child in the middle here, and then a right child here, and then, oops, sorry, I can't draw in the middle. Left child here of blue, right child here of that blue, and so on. You keep on doing the middle, and then you get a really nice balanced subtree if you do that rebalancing, which can be computationally expensive. But again, the idea here is to, let's spend some time to rebalance the tree so that every time we need a search, it's quick. And the third one is maybe the most interesting, but it's also the one I'm going to talk the least about, is we can deal with it with specialized binary search trees. So specialized data structures that are binary search trees, these are like AVL trees. Red-black trees are another example of these. I am not too familiar with them, but if you have heard of them, or you probably will eventually hear about them, these are some other ways of dealing with balancedness for trees. Because again, why does balancedness matter? I hate that word, but being balanced matters for binary search trees, because the more balanced it is, the quicker we're going to be able to search through them. The more they're going to have that big O of log n speed for those searching algorithms. And again, balancedness kind of means the bushiness, how wide it is. We want things to not be any taller, the height of a tree. We want it to be smaller if we can. And this is our technical definition, if you want one. That's pretty much it. That's all we're really going to say about this. That's chapter 5.